AP Statistics, Lesson 2.1, Visualizing Distributions. Okay, our objective today is that we will be able to recognize and identify the most common distribution shapes and identify some elements about them. The question that I want you to be thinking about as we go through this lesson is, what does my data look like? All right. We will also have quite a bit of vocabulary since this is the first session in the chapter. So here it is. Uniform rectangular distribution, normal distribution, bell curve, inflection point, standard deviation, skewed distribution, upper and lower quartiles, bimodal distribution, outliers, clusters, and gap. And I don't mean the store. Okay, so let's look at data. This is a typical data table. And even if you could read the numbers, and I don't expect you to be able to, you can hopefully see that it's a long list of a lot of numbers. And this happens to be the data of 252 men in the measure of their body fat. So really when you look at a table like this, you can't tell very much. You don't know what order it's in, you can't do any kind of make any inferences from it or anything like that. So, as they say, a picture is worth 1,000 words. And this is very true in statistics. So I'm going to show you a picture that represents the data. It's a dot plot, just like we were making in the last chapter. Notice that this dot plot shows us the data goes from 0 to 40, 41 it looks like. And there's a higher frequency in the middle, near 20 and maybe a little bit below it, than there is on the edges. On the edges it goes to a very low frequency. If I take a pen and I outline the frequency like I've done with the orange here, what I get is called a frequency polygon. Or if I make it into a more curved structure, it is a distribution curve. And that's what we're going to be talking about today, is distribution curves, mostly. So here, this is why we do it, because you can tell a lot more about our data when it looks like this than when it looks like that. All right. So there's several kinds of distribution curves. The first one is called a uniform distribution. Uniform distribution means all values occur equally often. And it usually is rectangular in shape. And so you can think of something that you might think is uniform. For example, the different number of students in each class at Ocoee High School. I'm pretty sure if you went and looked at that, they would all be around 700, 750, which would give us, if this were freshmen, sophomore, junior, seniors, it would give us a uniform distribution. But it wouldn't be exact. So mostly, and understand, no data is absolutely perfect, or very, very, very rarely. So what we usually say is that it is roughly uniform. If it's pretty close to 750 for all the classes, that would be a roughly uniform distribution. Okay, that's our first one. The second one is called the normal distribution. This is the one that we will probably be spending the most time with throughout the year. We do an awful lot. We test all kinds of things with a normal distribution. It is also called the bell curve distribution because the shape it makes is roughly the shape of a bell. And this happens because it happens when you do repeated measurements of the same or very similar items. So a bell curve might be the measurements of how big a penny is, or if you were measuring how long it took to mow a yard. Those things would be that if you did lots and lots of repetitions, you would probably come up with a bell curve or a normal distribution. Now, once again, we're talking real data often here, and real data usually only approximates a bell curve. So a lot of time in your questions, it'll say this data, which is approximately a normal distribution. Well, then we use the normal distribution. We don't worry about that approximately thing. We're going to use all the rules that we've learned for the normal distribution. Okay. Some things I want to tell you about it. When you have a normal distribution, the peak is, just like, since this is a frequency thing, the peak is the mode. So here is this line right here is the vertex, and that is the mode. Can't really see me write that one, so I'm going to write it in a different color as well. And the mode is also, if it's a perfect bell curve, it will be the same as the mean. So I'm going to also write the word mean here. So the mode equals the mean. And actually, if it's really a good bell curve, the mode, the mean, and the median are all the same. But when we talk about the center point for a normal distribution, we always want to use the mean, okay? Then if we're looking at the spread, how far apart are your answers, we have another word called a standard deviation. The standard deviation is the point of inflection. Now, an inflection point is where the curve goes from being concave to convex. It's kind of that breaking point between concave and convex, and it's just about there. It's kind of hard to see, and mathematically we won't be doing it. We have a formula to do it, and on this side it would be about here. Since it's symmetric, it's going to be in the same place. So this point is called, the distance from the mean to that point of inflection is called our standard deviation, which I'm abbreviating by SD. Notice there's one standard deviation on this side, it's another on this side. Okay, but the standard deviation is the distance between the mean and the point of inflection. Okay. The reason this is really important is the standard deviation is considered to give you 68% of your data should lie within the standard deviation either side of my mean, which means this area that I'm going to shade in contains 68% of my data. 68% of the data points are between here and here. Okay? Which means the other 32 are somewhere out in the tails. That's a very important part to remember, and I'm hoping you wrote that down. Okay, but we're going to, before we go on to the next, I want you to take a look back at my original data from the body fat percent. Notice, and this is a good example of where you get an approximately normal distribution. This also is relatively symmetrical, and my mode is actually here. Median is actually probably a little bit beyond that, but so right in here is where I would consider my mode, and then my standard deviation is going to be, well, I could do 68%, but it's going to be somewhere in here where the point of inflection is, and that would be about 68%, and then the rest of the data is on the outside. There are a lot fewer data points over here and here than there is in the middle, the 68%. And that should show you a real set of data that approximates approximately normal distribution. Okay, next kind of distribution is a skewed distribution. Okay, if our normal distribution, which I just showed here so that you can get an idea of the difference, if our normal distribution is symmetric, our skewed distributions are not. What happens is you have a tail that kind of drags out, And depending on what side the tail is on is what side you skew to. So this one has a tail to the right, so it's skewed to the right. This one is skewed to the left, and the tail goes to the left. And if you notice, it kind of looks like the same kind of curve, it's just that it has that tail. So I can usually describe my skewed curve as the normal part, and this part's the normal part, and the abnormal part of the thing. So data that happens in this tail is called abnormal data. Okay, doesn't really go with the rest of it. Usually when you see a skewed data, that means, and especially when you've got this part that's really near kind of a wall, it means that there was an ending point to your data, an absolute end, and all of it bunches towards that, and then kind of decreases from there. For example, when I have test scores, I usually have something that skews to the left here, where this over here is my 100%, and my B's, and I have B's, and then the A's, well, the A's are up here, the B's are here, the C's are in this range, and then I have a bunch of, or several scores that continue to go towards this way, and usually, the F's, there aren't as many of them, but they are over here, and they happen. The really low scores happen too, unfortunately. So that's an example of data that would skew left. Now, when you're talking about skews, you are going to, instead of using the mean, because if you look at this, you'll see my mode is here, mode's still here, but the median and the mean both shift a little bit towards the tail. Instead of using my mode for my center, I'm going to use the median. Here's my median. Median tells me where the center of my data is. And then I also use something called the upper and lower quartiles to describe the spread of the data. The upper quartile is just, if I would just took at the upper half of the data and find the median of that, I would have my upper quartile, which is probably going to be right in here somewhere. Right here. Unfortunately, it looks like mode. It isn't mode in this case. It's upper quartile. Upper quartile. My lower quartile is just the median of the lower half of the data. So I'm going to look over here, and my lower quartile is probably up in this range, because remember, there's not very many data points down here. So it's pretty close to my median over here, my lower quartile. So the lower quartile. Usually I abbreviate these with LQ and UQ. Now, don't worry too much if these quartile things don't make much sense to you, because we're going to get to them a lot in the next section. But that's how we talk about skew distributions, is with the upper and lower quartile. Okay, last distribution is called a bimodal distribution, and I have the bi part underlined, and that should tell you right there what's going to happen. That means it has two modes. And modes are most often, so here's my first mode, here's my second mode. It is two peaks. It often happens when the data includes two or more groups. For example, if you're looking at the height of American adults, you will probably get one group for the guys and one group for the girls, and they'll have bimodal, because women are generally shorter than men. Not all of them. I know that's a general statement, but it will probably give you two modes like that. And if you end up with data with two modes, you should be looking for, okay, what happened here? What is different about this set of data versus that set of data? Okay. And within this, you also have some other things happen. And these things can actually happen in any set of data. You might have outliers, gaps, and clusters. Okay? Outliers are the guys, or the data points that stand apart from the rest of the data. They're way out on their own, either too high or too low. And there are mathematical ways to test if something is a true outlier. Often outliers can be things like typos. They might be because when they did the experiment, something was not measured correctly. Those tend to be what your outliers are. However, every now and then, they are actual, authentic outliers, and they may point to something unique happening within your data. Or they might just be an outlier, and that's okay. Gaps and clusters don't actually have a definition. I kind of made one up for this. A gap is a break in the data. There is nothing to say how big that break has to be, but if there's a visual break in the data, that's called a gap. And a cluster is where a bunch of them go together. Like these are all clustered together. And once again, there's no actual definition. Well, you have to have 3 points to have a cluster. Some people call an outlier a cluster by itself because there's a gap between the rest of them. And once again, when you have clusters like this may mean something significant, and you need to look further into the differences in those groups of data so that maybe there's something going on that you didn't expect. Okay, well, we will have some activities to hopefully help us identify the different kinds of distributions and how they happen, and I will see you in class.